so let's now look at.
Have you got your microphone on?
Oh no, it's blinking red. Is that okay?
Not necessarily. No. Let's see.
It's like a call to action, but a clap to action.
No, I haven't.
It's not high bass, I don't really like.
Look at this. I think that means it's running out of gas, but you don't.
But that is also red.
Yeah, it's red solid, that's what you want. Not red thing.
Okay,
What do
so
you think
we
so
have
far?
looked at the Hamiltonian, and now I want to, Alan Ruttenberg has asked me to basically skip, I will not skip it, but break here and show ontology of physics. I think it's not the right order, but if you can't come tomorrow, Alan, then I'm willing to do that now.
I was planning on coming tomorrow. Just,
Yeah?
yeah.
So then I know what I do. I will do the ammonia molecule at the MASER, and then I will do, because it belongs together, then I will do ontology, and then we get back to the hydrogen molecule. Okay? So, and the dyes are a good example for what you can do with quantum mechanics. Yeah? So I mentioned already. So this is a graphical simplifying depiction of the ammonia molecule, which is a nitrogen atom with 3 hydrogen atoms, and these are indeed these are wrong, but these are of course right. So there are covalent bindings between the hydrogen atom and the nitrogen atoms. The reason why Feynman is depicting it like this is that he wants to show the symmetry plane of the atom, because the atom has 2 states, the molecule. In this state, the nitrogen is up above the symmetry phase formed by the 3 hydrogen atoms, and in this state it is below this plane of symmetry formed by the nitrogen atoms. And so, of course, this model is he writes himself totally wrong. So the true model of the ammonia molecule, and we will get back to this later, is an infinite dimensional Hilbert space. So it's infinite, and here we have just two dimensions, 2 states, so 2 dimensions of the Hilbert space. So it is a grossly oversimplifying model. And as I said before, it is mathematically impossible to calculate using the Schrödinger equation. It's mathematically impossible to model the ammonia molecule properly. But looking at this again, if we have just 2 states, we have a 2 times 2 matrix that we see here with state H11, H12, H21, and H22. And now if we plug in the 1s and 2s for the i's and j's, we get 2 differential equations. We get either I can be 1 or 2, so we can get these 2 left-hand sides of the equation, and then we get H11 times C1 plus H12 times C2, or H21 times C1 plus H22 times C2. So these are the 2 differential equations we obtain to describe the energy state of these 2 states of the ammonia molecule. And now you can say, well, wait a minute, where do all the infinite dimensions come from that it can? Well, each of the atoms is shaking in all kinds of manners. Inside the proton, inside the atoms there are protons which are shaking, and neutrons. I mean, not in the hydrogens, but in the ammonia, in the nitrogen, there are also protons shaking. So in all of these create state variables, right? So we have an infinite amount of state variables of what can go on in this molecule, but for the purpose of what we are going to look at now, the 2-state model is sufficient. So Ali, you said it's wrong. Of course it's wrong, because it's 2 states only, and the real model should have an infinite number of states. But this is a very important thing about physics. Most models of physics are wrong in this sense, however, they can still be adequate for a certain situation. And for the situation that we are going to discuss now, this model is totally sufficient. And so again, from the painting, what he should have done is he use here the dotted lines and here solid lines. So the solid lines are covalent bounds, and these are indeed covalent bounds. And I just looked it up, Alan, to make sure I don't say any nonsense. But these here
Bonds.
Bonds, yeah, covalent bonds. And this is just the plane of symmetry. So moving on, we see now the two states, and yeah, Feynman says now this molecule, like any others, has an infinite number of states. It can spin around any possible axis. It can be moving in any direction. It can be vibrating inside, and so on and so on and so on. It is therefore not a two-state system at all. But we want to make an approximation that all other states remain fixed because they don't enter into what we are concerned with at the moment. We will consider only that the molecule is spinning around its axis of symmetry, as shown in the figure, and that it has zero translational momentum and that it is vibrating as little as possible. Yeah, and so this is, so when it's spinning here, it's state 1, and if it's on the other side and spinning, it's state 2. And so Nancy Cartwright in her great book, Why the Laws of Physics Die, called physics as theater. Yeah, that so many of the real conditions are removed until you can come out and say, ta-ta, these are the equations. You know? and so like in the theater. And basically, so here we see it again, we have psi, and now this is called quantum superposition. You see here that the psi is basically a mixture of the base states 1 and 2. Yeah, so we have here psi is basically the likelihood of psi in going to phase to state 2, and this likelihood, and together they form the superposed amplitude of this state. Now, the base energy of both states can be assumed to be equal, and also the state transition can be said to be equal. So now, how do we get the Hamiltonian? Yeah, that's always a question. If I have a big Hamiltonian, it gets harder and harder. But here I have just 2 times 2 Hamiltonian. So how do I get the Hamiltonian? Well, it's assumed that this at this state, sorry, that's H12 and H21, yes, that they are also the same, and therefore that they get the variable minus a. And now if I use this Hamiltonian and plug in for H11 E0, for H22 E0, and so on, I get the differential equations are E left-hand side equals E0 times C1 minus A times C2, or A0 times C2 minus A times C1. And so the solutions of these differential equations are given here. I will not discuss them, they are a bit harder to find, but these are the solutions. So if you plug back in C1 and C2, so if you plug back C1 in here and calculate, and C2 also in here, and calculate all through, both sides of the equation will be the same. So these are now the equations that give us the amplitudes for the 2 states depending on time. And so these are waves, as you can see, because they have here an exponential and complex number, so these are 2 waves. And so what do these solutions mean? So let's look at these equations. We don't have to understand how they come about. But so if b equals 0, then then we have just the first term, right? Because if I put in here 0, this all gets 0, and then then I have just the first term. The first term, as we see, is exactly the same. So if they are both, if b is 0, both terms have the same frequency, namely omega equals E0 minus A divided by H, by Planck constant. If everything changes at one frequency, it means that the system is in a state of definite energy. Here the energy is E0 minus A. So there's a stationary state, and this energy is in which the 2 amplitudes C1 and C2 are equal. Yeah, so this is a stationary state. When B is 0, they have a stationary state in which the amplitudes are equal. And we get the result that the ammonia molecule has a definite energy E0 minus A if they are equal amplitudes for the nitrogen atom to be up or down. Up means the N is above the plane of symmetry, and down means it's below. If A equals 0, both amplitudes then have frequency E0 plus A divided by the Planck constant. So if these terms go away, I have plus B B divided by 2 and minus B divided by 2 times this, but the energy is the same of both. So there's another state with the definite energy if the two amplitudes are equal, but they have the opposite sign, and that's here. So because if A is 0, then I have here a positive sign, here a negative sign, and the rest is the same. So that means that C2 is then minus C1. And because there's some chance that the nitrogen atom can flip from one position to the other, the energy of the molecule is not E2, E0, as we would expect, but it's either E0 plus A, which is this one, or E0 minus A. So when it flips, right? So now there are two energy levels. And so in this highly idealized model, the two states of the ammonia molecule vary harmonically with time. So here I saw, as told you already, time is now modeled in units of pi. But no, it's actually modeled in units of this pi fragments multiplied by the Planck constant divided by A, just to have a nice plot. So physicists very often radically alter the axis of their plots to make the plots really look nice and well understandable. But basically that's the passage of time. And you see here the two states of the molecule. That is the probability that an ammonia molecule is in state 1 at T0 and P2 that is to be found in state 2. So at here, when there no time has passed, it is 100% probability to be in state 1 and 0% probability, and then the probability over time, the probability of the first state drops and the probability of the other state increases. And so here again, if I have these, so if the ammonia molecule is mathematically like a pair of pendulums, it's basically like a pair of pendulums. And there are the two frequencies E0 minus A and E0 plus A divided by the Planck constant. Here again there's a mistake I want to correct so that when you get the slides you will not have it anymore. That's because I didn't reproduce all the equations in LaTeX myself, so some are broken, which I just copied from the book. But if you pull the nitrogen to one side, then you get a superposition of these two frequencies and you get a kind of beat node because the system is not in one or the other states of definite energy. The splitting of the energy levels of the ammonia molecule is strictly a quantum mechanical effect. Yeah, so this is basically what's happening. So these are the two, this is now sinus and cosinus expression of the two solutions that we have seen on the last slide, and now you see that they're moving like two pendulums against each other, so to speak. And when one pendulum is swinging up, the other is swinging down, and vice versa. And so if you square, so this is just to show how you get this graph by squaring, of course, the amplitude to get the probability. And then you have here, what is plotted here is the square of this, because otherwise you wouldn't get something between 1 and 0, but you would have complex numbers. So this is basically a very nice model so we make an artificial model of the system, we simplify it, we get a very simple Hamiltonian. We use the Hamiltonian to calculate we set up the differential equations with the Hamiltonian, and then we calculate the amplitudes of the two states and understand, and then we can understand how the system is behaving. Good. So now we can build a quantum device called a MASER, which was the precursor of the laser, which is exploiting this. So now that's why I'm showing this. So we have basically a super simple model of a molecule, the ammonia molecule. And we know it's wrong. And we have basically, if we know that it has an infinite number of dimensions, it's true Hamiltonian. Now we've just taken 2 dimensions. What is usage of this? Why do we do this? Well, if you look again now at the molecule, you have energy difference between the states 1, and so we know that the energy of state 1 is E0 plus A divided by the Planck constant minus E0 minus A divided by the Planck constant. And if you calculate this out, then you get 2A. And 2A is 10 to the minus 4 electron volt. So this corresponds, and so if you look at our table for electromagnetic radiation that we had before. So, and we look here, 1 centimeter, so 10 to the minus 4 electron volt is a wavelength of 1.25 centimeters. So this is a logarithmic scale. So you have 1 centimeter, 10 centimeter, 100 centimeter. So somewhere here is the wavelength, and this is really the wavelength that you use in your microwave oven. Yeah, and so this wavelength is basically the wavelength of the energy of the photon that is emitted when you switch the state of the molecule. And so what happens, the ammonia MASER is a device to generate a perfect microwave electromagnetic wave at 24 gigahertz by using the quantum states of the ammonia molecules. So this is also, if you look at how many gigahertz these are, we are here, right? And so this is 1 gigahertz is here, and so here this is already 10 gigahertz, and we are now here. That would be 100 gigahertz, and we are somewhere here. So this we have 24 gigahertz of frequency, and so so what we see here is that we have different dipole moments. So this is a kind of a bit like the magnetic moment we saw before. It's an electrical moment that comes from the distribution of the electrons. So you know that these here are covalent bindings, and there's more electron density here than here. So there's a positive field in this direction from minus to plus. And the same is here. If the nitrogen atom is below, there are more electrons because it's attracting the electrons of the hydrogens in the covalent binding. So then the dipole moment, which indicates basically electric field within the molecule, is showing in the opposite direction. And it's modeled here. This is the center of mass of the molecule, and so basically the dipole moment is modeled to point from the center of mass towards the field. Now we have again something like the Stern-Gerlach apparatus, that we can now build a device that can split the two different energy levels of the ammonia molecule in an electric field. So here we have an electric field, and this electric field, with increasing electric field, we can split the two beams. We can create one beam of ammonia molecules, and this electric field, because it's acting on the dipole moment. Here, remember, this indicates a field within the molecule, and now this electric field that we apply from the outside attracts this state to one direction and repels this state. And so, by putting, now we don't use a magnetic field to separate the molecules. Do you have a question? Oh, okay. By now we don't use a magnet anymore to separate the molecules, but now we use an electric field. And now the one type, so this energy level goes here, and this is the high energy level. It's E0 plus the root of A squared plus mu squared. So now you see that the electric field energy is added to the energy that the ammonia molecule already has, and here it is subtracted, right? And so so this expression is subtracted, and now you see this is its electric field through which it goes. So here the molecules come through a slit, and here there's an increasing electric field, and the two energy levels of the ammonia beam are separated by the electric field in which there's a gradient perpendicular to the beam. And so, in other words, the molecule in state 1 has an energy which increases with E square, and therefore this part of the beam will be deflected towards the region of lower E square. And the molecule in state 2 will, on the other hand, be deflected towards the region of larger E square, since its energy decreases as E square increases. So you can now separate the molecules into two beams. And now here, so beam 2, let's remember, is the one with decreasing energy. Beam 1 is the one with increasing energy. So now we have two beams. This ammonia beam of molecules is discarded. It's really thrown away. By the way, ammonia is really, doesn't smell really nice. I think I smelled it. And this beam is kept. And now we have here another electric field. So we had an electric field here. We have here another electric field which is called the MASER cavity. And this field contains an electromagnetic field at a certain frequency, O0. And now the beam is going through this field, through this cavity. And it sends through a resonant cavity. The other beam is discarded. Inside the cavity there will be a time-varying electric field. The molecule enters the cavity field, oscillating at the frequency O0, exactly right, induces transitions from the upper to the lower state. And so if you, now there's resonance between the molecule and the magnetic field, and this induces the state to fall back into the lower state. And so the energy that, when this happens, of course, energy is freed, and this is released into the field. And so, in an operating maser, the molecules deliver enough energy to maintain the cavity oscillations, but not only enough power to make up for the cavity losses, but even providing small amounts of excess power that can be drawn from the cavity. So basically, you can also get energy out of the cavity, and this energy that gets out of the cavity is light. So the molecular energy. So I have now here the mixture of states. I take the high energy state, deplete its energy, and a part of it is used to feed the oscillation. Another part of the depletion, I actually transform the molecular energy into electromagnetic energy. And this energy I can use, and now a perfect microwave. This energy will come. This was first a chemical energy, will come now out of the maser as a perfect microwave of exactly one wavelength. And this is quite fascinating. Now this is just a bloody microwave. What to use it for? Well, we use it today for atomic clocks. So because its frequency is so perfect and pure, we can use it to time atomic clocks. But there's another device that you've all heard. It's a laser. You have one. It's a quantum device. You have one there. And this laser also produces light of only one frequency with a similar mechanism. So the laser is a bit more complicated, and therefore I won't explain it. But it's a similar principle. So what you can see here, how the quantum state understanding of the two-state system can be used to calculate the energy difference between the two states. Then the energy, then the dipole momentum can be exploited, or dipole momentum, it's called dipole moment, can be exploited to separate the two molecules, and then the one with the high energy can be used to convert its chemical energy, so to speak, into light. And this is, I think, really fascinating. And what is now we come to the point why I think, Alan, we need to do this chapter at least before doing the ontology part, is that quantum mechanics cannot calculate E0 and A for the Ammonia molecule. They must be measured. Why is this the case? So in the discussion we have assumed values of E0 and A without knowing how to calculate them. According to the correct physical theory, it should be possible to calculate these constants in terms of the positions and motions of all of the nuclei and electrons. But nobody has ever done it. Such a system involves 10 electrons and 4 nuclei, and that's just too complicated as a problem. As a matter of fact, there is no one who knows much more about this molecule than we do. That's still true. All anyone can say is that when there is an electric field, the energy of the two states is different. The difference being proportional to the electric field, and we have called the coefficient of proportionality 2 mu, but its value must be determined experimentally. We can also say that the molecule has an amplitude A to flip over, but this will have to be measured experimentally. Nobody can give us accurate theoretical values of mu and A, because the calculations are too complicated to do in detail. And they are not only too complicated, we can't do them with a computer, really do them with a computer either.
No,
So
that doesn't say it's impossible. It says you don't know how to do it.
yeah,
It's too complicated.
he says it like this, but from mathematical theory of differential equations, of partial differential equations, it has been mathematically shown. With the mathematics, we have the total apparatus, we can't calculate it because there is no solution space defined. You would need thousands of dimensions, and so the partial differential equations would involve thousands of dimensions. So the most difficult that can be approximated today with a reasonable satisfaction includes 7 or 8 variables. We would have thousands of dimensional space. It's absolutely clear to every mathematician and every physicist that thousands of dimensional spaces we can't find solutions. And if you read a textbook of functional theory, you will see why. It has been proven that for such high-dimensional spaces, partial differential equations don't have a solution space. And that's because of the way partial differential equations work. They work by always differentiating one variable after the other. But if you have too many variables, this system of differentiating first for the one, then for the next, and the next, doesn't yield an adequate description of the behavior anymore, because the influences in the system can't be modeled with the partial differential equation trick. The partial differential equation is an infinitesimal procedure that works in low-dimensional spaces, and it's mathematical knowledge that in high-dimensional spaces we cannot create adequate. We have no solution space for these systems of partial differential equation. And that is what we saw as a system of partial differential. It's a system of differential equations. It's actually not partial because we have to differentiate, so it's ordinary differential equation, because we have to only differentiate by one variable by time. But it is still but it's in the high dimensionality we would get if we wanted to calculate these values that are in the matrix by hand. We couldn't do it. Tom.
So basically what you're saying is, so if I understand you properly, so you use differential equation in order to guess world lines, or to compute world lines, right? So you're saying that
States
exists a world line which describes the systems, right? But we can't use the tools of differential equations in order to compute this world line.
Yeah, or state change in quantum mechanics. You don't say world and quantum mechanics, or state, sequence of states or state change, you would say.
But I think your point is that there exists a world line, and this world line has a definite description, right? Mm-hmm. So, but it's a different question than, well, it's independent from the fact that you can't guess or compute this world line using differential equations. Right.
But quantum mechanics.
I can believe that. Right.
But the implication seems to be that the Schrodinger equation is not valid because
No, it's valid for the scope for which it was made, and the scope is a few variables. It just. I mean, why is there
Well,
Well,
that's
that's
fine.
dated this equation according to code. So there are nicer ones.
Yeah, so there are three big systems for quantum mechanics. There's the Schrodinger equation was the first one, which deals with fermions. So spin 1/2 particles, but it can also deal with spin 1 particles, but it can't deal with bosons. So it can only deal with fermions or other particles that are not transmitters of the interactions. And only a few particles. The second important is the Dirac equation, which deals with bosons, but only also a few bosons, like one photon. And then there is the third, and since the 50s and 60s quantum field theory was developed, and that can deal with big amounts of particles, but with a totally different approach. So it doesn't use the Schrodinger equation anymore. And we will not look at how it works, but it's too complicated for this. But it works with different. But it was very clear from the beginning that the Schrodinger and the Dirac equation are only adequate for events with very few particles. And the ammonia molecule is such a good example because it shows that even though the model is not fully adequate, it led us to build an ammonia MASER. It gave us sufficient understanding of what's going on in this molecule to build such a machine that can translate, that can filter molecular properties, quantum properties, and then can exploit them to create a perfect electromagnetic radiation. I think this is incredibly impressive, and that it can't be done. That we cannot calculate the numbers that are in the Hamiltonian, that we can't calculate. Sorry, yeah, these are the variables I wanted to show the. That we cannot calculate these. That is nothing to be ashamed of, right? It's just that it's impossible because the mathematics don't allow us to do that. But it doesn't mean that the Schrodinger equation is wrong. It's just the ammonia molecule is just too complicated for its scope. And so, because this is so, of course, all the debates in philosophy of physics, is the Schrodinger equation universally valid and so on? They are wrong because of course it's not universally valid. It's an ordinary linear differential equation with complex numbers. That's all it is, and it was invented to describe particle motion. And this can do for a few particles really well, and it can also describe this motion of this flip state. So that based on this, the machine could be built. I think it's a great achievement, but it shows also the limitation of these models. So, are there any other comments or questions regarding this device? The Ammonia and the Ammonia MASER. Okay, so you've now understood the first quantum device. So we have achieved much more than I thought we could so far. And now I want to, we can skip all the rest and go to the ontology. However, it might mean that on Monday we'll repeat the ontology once more, because then we will have understood more. Does it make sense, Barry?
Yeah.
So the ontology part, for many of you are interested, I know, in ontology of physics, it's very short, because it only gives a glance at how Barry and I plan to go about quantum ontology. So we believe, and this is the work that we've done so far, that BFO is about common sense reality. And it's about, and so typical content of BFO are positive science entities, like we have in medicine or biology, and also it can only contain universals. So a universal is an entity that has always an individual instance. For example, we are here all individuals of the entity human being, and human being is a universal. Then we have a physics upper ontology, which is not the common sense reality of BFO, but which is reality modeled using physics. And it is a mixture of universals from BFO and a priori entities from mathematics. So what are a priori entities from mathematics? So these are entities like, for example, the number pi. The number pi is a well, let's start with another entity, the entity 0 and the entity 1. These are atomic abstract entities, and pi is, for example, a structural entity or relational entity, structural entity that is purely mathematical. There is no pi without human beings, and there is no pi in reality. Yeah, pi is just the relationship between the circumference and the diameter of a circle, of a perfect circle. There is no perfect circle in reality. There are circles in reality, but there are no perfect circles in reality. And pi only arises when a human being looks at the circle and measures its circumference and divides the circumference by the diameter, then, or 2r, then you obtain pi. Now, why is there no pi in reality? Because to print it out, you would need to calculate forever, because it's an irrational number, so it goes on forever, you can't instantiate it. And it's really just, it's an ideal entity, an a priori entity. Physics takes entities from BFO and entities from mathematics and uses both to model reality. And mathematics doesn't have any universals. So mathematics contains only a priori entities, it's free of universals, and it contains those entities in their structures. And so we obtain the physics ontology by combining it in this way as it's shown here. And the lower level physics ontologies then will be classical mechanics, electromagnetism, general theory of relativity, quantum physics, solid state physics, and so on. So this is how it will be structured, yes.
So what is the group then?
The what?
A group, the structure of a group.
The group in mathematics, it's an algebraic structured entity. So Wesenszusammenhang, that means it is an entity that is obtained by composing other entities together. Or a manifold is also something like this, right? A manifold, Riemannian manifold, is also a mathematical abstract entity.
So I just, why is it not a universal?
Because there are no instances of any of these. There is no circle in reality, or there is you can model the surface of the Atlantic Ocean as a Riemannian manifold,
But
right? But it is not a Riemannian manifold.
And the natural numbers wouldn't be an
Yes.
instance of a group?
So the natural numbers are always a point of contention. So when you discuss with philosophers of mathematics who believe mathematics contain universals, they always bring the natural numbers. My argument, yes, of course you can use the natural numbers to count, and the natural numbers are related to reality, but in my view, the natural numbers themselves are also mathematical entities.
So I don't think there are many people who embrace the view that natural numbers have instances.
Oh, but the whole in the analytical philosophy, they think
Well,
that
what
every
would be-
mathematical entities are empirical entities.
Yeah, but
There's a whole
to have
school saying it.
instances, that's
What?
the thesis is that the thesis you were discussing is the thesis that that numbers have instances. I don't believe that the number 3 has any instances.
Yeah, so do I.
And I don't believe that many people do. I think that's not the issue. The issue is whether they are empirical or whether they're identical with sets or whether they are identical with groups. Groups in the sense of collections, not
Let's
groups.
take groups. So is there a term group?
Yeah, in algebra.
Okay, and then there's particular groups, yeah?
There are
No,
types of
And
groups.
what's
Subtype.
the relationship between a particular group and group?
So a particular group is a type of group. So if you add more properties, you get, of course, you get more, it's a specialization, so then you get a more complicated group that is that's a subset of the concept of group, right? But it's still, you don't get an individual group. There is no group in reality. I mean, in the algebraic sense.
I'm not talking about reality yet, I'm just talking about the structure. So I'm trying to understand, there are particular groups, and there is the term group. And there's some
No, there's no.
relationship.
The group.
The Rubik's Cube group, right?
What?
The particular
A
group
billion
that's
group.
instantiated by.
Let's say
by-
a billion group.
What's that?
Abelian group, that is type of algebraic group. So there is an abelian group and there is a general notion of a group. And the abelian group has just more.
Specialization though is always in terms of sets, right? Specialization means a smaller set.
Yeah, mathematics is
What do you mean by
basically.
specialization here?
Yeah, I mean that it is.
What are the elements of the set, in other words?
So the elements of the set would be abelian. So now you can say you have the notion of a general abelian group, and now you can have examples of abelian groups, and these are of course members of the set of abelian groups.
But each of those is a type, according to what you say.
Yes. Yeah, I mean,
So what are
no,
theirs?
sorry.
So what are theirs? What's the set they are?
So let's take something
I
that
mean, it sounds
everybody.
like it sets all the way down except never any members.
No, that's not true. So 0 and 1 are so to speak they are primitives, right?
I don't want to talk about 0 and 1. I wanna
You
talk
need
about- I
to.
wanna talk
So
about-
you need to, because without 0 and 1 you cannot build up mathematics. So every mathematical axiomatization starts with 0 and 1. So you cannot say I'm not talking about 0 and 1. If you don't, then you cannot talk about
But
mathematics.
I'm asking a particular question, right? The relationship of what you call particular groups or in something groups, and the more general term, let's call it just a term. And you're saying it's a specialization relationship. And a specialization relationship is a relationship between sets. And therefore there has to be members of the set.
Yeah.
But every group you're saying is a type. And so I don't know what the member of the set is. There's no members of it.
Of course,
Or
because
what you're saying.
the mathematics are only types, and so the members of the sets are the most primitive types there are the monadic entities like the 0 and the 1. And mathematics is axiomatized always with set theory. There's no other way to properly axiomatize mathematics. So you start with the most primitive elements, which are the numbers 0 and 1, and then using the set operators and other constructive relationships in mathematics, to which we'll get on later slides in more detail, you build up the entire realm of mathematics. And then but you never have individuals, because an individual is something that exists in reality.
Oh, by definition.
Yeah.
But
Yeah.
That's, again, it's sort of a separate.
No, it's not separate. So that's the reason why mathematics cannot be part of BFO, because it doesn't have universals. So it's not. It is the core feature why mathematics is not a part of BFO. It can never be, because it can't have. It doesn't have universals, and something that can't have universals can't be part of BFO. And that's the core argument, right? I mean, if it would, so then if we would make mathematics a part of BFO would stop being an Aristotelian ontology.
So,
it can't
Alan,
work.
do you think that the circular things that we see around us in reality, for instance, the bases of water bottles and so forth, are instances of a universal called circle?
No.
Good. Okay, then you're on our side.
But what I was trying to get at is that there was structure that we call universals and instances, which by definition we're saying have instances around, there's certain specialization structure.
Sorry.
Right? That is our.
No,
That's
this
in
is
BFO.
relationship, it's
That's
not
BFO, but-
specialization.
And it sounds like there's also that kind of structure, maybe.
No, because
No, you're wrong. Instance of is not specialization of. It's two different
But I
relationships.
understand, you
Yeah.
said there's only specialization.
Yes.
Well, specialization implies sets, so I'm trying to
Yeah.
understand what the members of those sets are.
Most of them are still structures until we get down to 0 and 1. So for example, I'll give you a simple example that everybody in the room can understand. A circle, I give you the definition of circle and line in set theory. A circle is a set of all points, it's an infinite set of all points that are equidistant from one given point. That's a circle. Or a line is a set of all points that are such that if you choose two of them, their distance will always be minimal in Euclidean space.
So you just use those, something that has instances, you use the word point,
Point has no instance.
and yet you said it's a set of all points.
Yeah, but it's a set of.
Is a point one thing or many things?
So
You just use it two ways.
No.
One as
He's right.
point, a term.
No.
The other is the set of points.
a set of so
And that sounds like a universal instance relationship.
No,
Aside from the constraint that instances must be.
Okay, let's analyze the sentence once more. You didn't understand it, so let's only take the circle.
Okay.
A circle is a set of points that are equidistant from a given point.
So there are things called points.
Not things, mathematical abstract entities called points, and they can form sets, but they are no individuals.
They're not types.
Calling them types or not doesn't change their nature. They are abstract entities. You can call them types or not, it doesn't matter. But they are not types in the sense of BFO. They are abstract entities, and they can form sets, although they are not individuals. So mathematics has many sets of entities which are not individuals.
And the basis of saying they're not individuals is simply that they don't land up grounding out in a material entity.
So that they don't exist in reality.
they don't have a spatio-temporal
They
location.
don't have a spatio-temporal extent.
Yes.
Right. There's other things that don't have spatio-temporal
Yes.
extent.
Thank you.
Like justice.
Like dispositions.
Dispositions certainly have a connection to the material bearer of the disposition, and the
Right.
bearer
So
is in space.
It's a different kind of justification.
And in
for
time,
calling
indeed.
something
Dispositions have a starting point, even though it's vague typically.
Right, so that's grounded out in material entity.
Yeah.
That's how I
Yeah.
describe that.
And mathematics is not grounded out in material entities.
You have another question?
Yeah,
Yeah.
not I just
That's
have a
like to be
question. I
argued.
just want to point out that the definition of circle you just given also refers to the spheres or higher dimensional spheres. So you need to add this dimension.
Yeah, no, how to do with the mathematics is that you have the symbol C, and then you add more, have a natural number as an exponent. I agree with you, but I only gave the dimension, the two dimensions. So, yeah, I
We
mean,
just built up extra structure on top of the, beside BFO, and we still can't answer the question where light is. So this is
I
a
think,
problem.
yeah, I think really, I
That's
think,
what I would hope the ontology of physics would help me answer.
yeah, it will. I mean, the idea is very simple. The idea is to model this ontology like physics works. In physics, you choose a system you want to describe. Then you have magnitudes that occur in this system that you need to describe the behavior of the system. Yeah, like these are the magnitudes you need for weight on the spring. And then you have a mathematical model that describes how these magnitudes are related to model what's going on in the real system. And you can do this for all systems. And let me show you an example. First, I do the mathematical entity, and then I show you an example how this works.
Yeah.
So here we have mathematical entities which are a priori entities without instances. And so I would like to manipulate this a bit, because this is not really ready and a very long discussion. So I will now blank this out. Yeah, it's not we can't do this here at the level that is adequate for the people in the room. So I need to do this another time. But if we disregard the way mathematics gets written down, yeah, if we just think of without written down mathematics, so I'm now thinking of pi equals c divided by 2r. What do I do then? Yeah. So then I have actually used a constructive relation, equality, to create the equality between the left-hand side and the right-hand side of the equation. I have circumference is I've created via my definition of circle that I just gave it, which you criticized for dimensionality, which is, for this I have used relations, yeah, or functional, that was a functional, which is a relation to define the circle. So the circle is somewhere here, down here, it's a structural entity, and the circle has property circumference, and now I take on the right hand side, I then take the circumference, and then I have the radius times 2, which is a line, which is also a relation, which I also defined as a certain set of points, and then I get to this with the constructive relation, the structural entities and the monadic entity, the two monadic entities which I have, I can then get to the equation pi equals circumference divided by 2r. And when I start to write them down, I get behind this box, but we take this because Barry and I have had very long discussions, and it's philosophically very complicated and not the right place, but basically that's the ontology of mathematics. And
so can I have a go with light?
Yeah, let me just
Okay.
do one more.
What is behind the box?
The way to write down mathematics.
Ah, yes.
So how you write down this equation.
Oh, so where does dimensions go? Mathematical dimensions, would they be under structures? Sorry, algebraic field?
Yeah, so a structure, so dimensions are certainly structural entities.
Well, would they be under algebraic field, or I mean definitely not relation?
This
Would
is
they-
not
So
meant
the
to-
so these are
remember,
examples.
These are just examples.
These are
Oh,
This
okay,
is not
okay,
meant
never
to-
mind then.
Many
Okay,
dots.
good.
Yeah. It's just to illustrate. This was done quickly for certain reason.
Fair enough.
And so the only thing I want to okay. So do your light example now.
Good. So you have to remember that this physics ontology is based on physical theory, what physicists are describing. And our argument is that physicists are describing, for specific reasons having to do with applications, abstract structures very much like.
The key idea is really to say that we have, these are equations, so the model is, the model also contains not only equation but also text, but the core of the model is the equation, and it relates to the system which is their reality via the magnitudes, and that is how physics works, and I think that is, so everything that is here under system can be described using BFO. Right, but why do we make system? So it says real, mind, independent, human, but human limited, also universal, BFO universal.
So electron in an electric field, that's a system, yeah?
The electric field is a system, and the one electron in the electric field, most physicists would say the smeared out probability that we call electron, is of course is one entity in that system.
Okay, so
But it could
we
be
still have
systems.
very real problems in that we have to get electric field and electron we have, but electric field is not in BFO either. And we have to, if we're going to be saying that we've dealt with physics ontologically, right, and we're saying that
No, we can't.
electric field is something in reality, then we still have a problem because our ontology reality is missing it.
No, I think that when we build out the physics ontology, we're going to have to introduce lots of terms. Many of them Jobst has already used today, which depict different kinds of physical systems. Now, many of those physical systems have counterparts in the BFO domain. And so in building out the physics ontology, we're also going to have to build out, to some degree, BFO. And actually, no, I'm sorry, we're going to have to build out CCO, because BFO doesn't have to get bigger. It may have to get bigger in dealing with things like beams and liquids and gases. I don't think BFO has an adequate,
It has to be expanded for field.
something like field, yeah. But field, so the term field in physics is vague too.
So no, it's not vague. The field of physics doesn't exist in reality. It contains two examples. It contains the harmonic oscillator as an example of classical physics, and the ammonia molecule that we just discussed as an example from quantum mechanics. And then you can see, and even these two have so many terms and variables that the paper would get too long if we all ontologize them. But we will ontologize with this scheme. I just built enough of them that I think that you will convince yourself that this is exactly right, and that this is kind of, I mean, the reason why I work with Barry is there are two reasons. One, he knows German and loves German philosophy, parts of it. And the other one
And
is that
hates German.
what?
and hates other parts of it.
Yeah, that's okay. No, and the other one is that I agree with that BFO is a fantastic ontology for describing reality. Yeah. However, physics has to make compromises, and we have to ontologically deal with them. So I would the second part of the ontology slides I have, it can only be understood once I've done through the quantum stuff. So now we'll go back to the quantum stuff.
Okay, so I would suggest that we have a break now.
Good. An electron and proton. And hydrogen molecule is made of 2 protons and 2 electrons. And you see here that you can say that electron A is around the first proton, electron B is around the second, as shown in the top half of figure 10. And then this could be called state 1, as it's shown here, and state 2 could be that it's vice versa. Then they call this is called state 2. And from the symmetry of the situation, those 2 possibilities should have the same energy. But as we will see, the energy of the system is not just the energy of the 2 hydrogen atoms. So what's going on here? So you see here again, the state is the sum of this ket multiplied with this operator.
So can you just go back? I didn't understand the distinction between state 1 and 2. Can you explain it again?
Just the 2 electrons get exchanged. So here you can see it.
Yeah.
And it's right, electrons have individuals.
But who could
Electron A and electron B, these are real things.
who could know?
Yeah, we come to this. So
Could be different levels of energy.
that's for a moment assume it. So when the protons are 3/4 of an angstrom apart, there is an energy minimum if the electron spins opposite. And this is, how could we know they have opposite spin? And so the spins try to reach antiparallel conditions to liberate energy. And if they do this, and this you can model with a more complicated model that shows that then gives a minimum, and that is indeed, if you calculate this model, which I'm not showing because 8 times 8 Hamiltonian gives 8 differential equations, and it's a big and complicated system, and it's hard to solve. But when you solve this system, then you will find that at this distance there's energy minimum. And so the spins, so if you have 2 hydrogen atoms with electrons spin up, they will not combine to a molecule. Only those will combine where one is spin up and spin up. Or if you force them to combine, then the one electron will change its spin to get spin down, and then they can combine. And that's a result of quantum mechanics and what you can also measure. And this is a case that this is one of the systems you can still calculate because it only involves 4 particles. You can calculate with the recipe we've looked at for that we've seen at the beginning for the ammonia molecule. But in this case, it's a realistic full model. And you find it in an advanced textbook of quantum mechanics in the later parts, because it's still very hard to calculate, but it can be done. And so this is just to give you another application. Now I have another nice application of the state idea of quantum mechanics, which is the 2 base states for the molecule of the dye magenta. So magenta is a very powerful dye. That is a chemical. That's a molecule of the magenta dye, and you see it has 2